In this subchapter, we're going to see about the irrotational flow, or we call it the potential flow. In the potential flow, the flow normally is irrotational. It's as many as in flow rotation. In many flow, there are rotational or irrotational region. But in this in this chapter, we studied only the irrotational flow. What is irrotational flow? If we studied the before rotational and irrotational flow, the previous chapter we studied that the vorticity is given by del cross V, which is this is equal to cos 0 if for irrotational flow. If rotational flow, this equation may not be equal to 0. So now, in this study, we're going to see the process or the what is we call it a potential flow, where in the potential flow we know that this flow, for example, we take the flow above the aerodynamics like this, or we call it the aero around the bodies. So we have the flow around the bodies, and then it's create the boundary layer here, and then this is invisible fluids, irrotational invisible flow regions here, and then the flow comes from here. So the irrotational flow normally is given by irrotational flow also a steady flow, and then it can satisfy the what we call it the Bernoulli equations given by these equations. All right, half v squared plus p divided by rho plus gz equals constant. This is a Bernoulli equation. So where c is the same everywhere. So it said c is same everywhere. If you have the lines flow like this, so if measure here 0.1 and then this is here 0.2, so we can see that the Bernoulli equations, let's say P1 over rho plus half P1 squared plus GZ1, this is equal to P2 over rho plus half V2 squared plus GZ. This is meant by this equation, which is the C are same is everywhere. So why why this happened? Because of we know that from the previous one I said explained you before that the delta cross V is equal to 0 for irrotational case. So then we can have this V equal to delta phi. So phi is a velocity potential. Right? Then we know that if for steady flow, incompressible flow, then we have the rho equal to constant. All right. So if the dot product for V equal to 0 and the dot product for delta phi also equal to 0, then if we simplify this one, we have delta squared phi equal to 0, which is this is we call it the Laplace equation. So Laplace equation. All right. So now we're going to solve this in two category. One is we call it the Cartesian coordinate. What is mean by Cartesian coordinate? If we solve any problem in like this, for example, so if this case we call it this is as a x, this is as a y, and then here z. These cubes we call it the Cartesian coordinates, where we read this coordinate as x, y, and All right, in this case, so delta squared phi equal to d squared del phi divided by del x squared plus del squared phi del y squared plus del squared phi del z squared. So if v equal to this, so we can simplify this one in vector form like this. All right. So what we can see here, we know that, okay, in I, in vector form, ijk is represented. This is also we can write like this. This is equal to u I plus v j plus w. This already we have seen this in the previous this in chapter 1. All right, now so therefore u can be written like u equal to here, and then we can define that v equal to this v dy, and z equal to omega is equal to dv dz. All right, so now in this case, maybe we only focus on two-dimensional, therefore we only throughout this course we only focus these two, u and v, because didn't see we didn't solve in this three-dimensional. Why? Because of we know that the string functions only string function only exists in two dimensions. Okay, therefore this one also only. Now we solve in the cylindrical coordinate. So cylindrical coordinate means that we have the cylinder like this. All right, so what we have here, we have in the r radius, and then we have a theta, and also we have in this way, this one we call it the z. Okay, r theta z. So the theta is the radial angular directions, r is the radial direction. So the potential flow here is given by delta squared phi equal to half d dr r d phi dr plus half r squared d squared del squared phi del theta squared plus del squared phi del z squared. So this is in the magnitude form or in the scalar form. This is in the scalar form, and then this is in vector. So again, we know that in the vector this is actually u, this is sorry ur, this is a u theta, and then this is the u z. So if that was the case, we have ur equal to d phi d theta, d phi dr, u theta equal to half del phi del theta. All right. Again, so maybe we're not seeing this in this topic because of our focus more on two-dimensional flow, which is involved u theta and ur only. Okay. Therefore, we also have d squared phi del x squared plus del squared phi del y squared, y squared, y squared. This is a square. All right. So this is equal to 0. So both phi or string functions and potential velocity satisfy into the Laplace equations. So we must satisfy only the 2D Laplace equation for both potential flow and string function, or potential velocity and string function. Okay. Moreover, we have d phi equal to del phi del x dx plus del phi del y dy. So again, if we solve this, del phi equal to u del dx plus v dy. So if phi is a constant, so we have u dx plus v dy equal to 0, and then this again, we can see that the same equations that we have seen here as we compare to the previous one, okay, in the stream function. So we already know that um, eh, for this case, we already know that uh, phi equal to constant, okay, psi equal to constant. This is the stream function constant. Then dy dx equal to v over u. This is a streamline constant phi lines. And then we have dy dx equal to minus u over v, which is this one we call it equipotential line, constant phi line. Okay. Later you can see the example of this in my video. Okay, please get my video and then watch it for this example. All right. Okay, next we're going to see the relationship between the stream functions and potential flow. We recall that the string functions in any any string function only exists in the 2D flow, and then phi on the other hand is exists in the 3D flow. So we know that this is only exists in 2D flow, where this is exists in the 3D flow. Let's we concentrate on the flow, which is a constant density. So we have the psi required 2D flow, okay, required the 2D flow, and then phi required e-rotational flow. To use both phi and psi, we must satisfy these two conditions. If one of these not satisfied, so we cannot use potential flow. Alright, so now we have u equal to d psi dy, v equal to minus d psi dy. Since the flow is e-rotational flow, and then we know that delta multiplied by v should equal to 0, which is we know that the vorticity equal to 0. Therefore, we have dv dx minus du dy equal to 0. Alright, so now we substitute back into these equations, and then this we get the similar for equation for the string function, which is this is Laplace equations in two-dimensional for string function. So if you draw this line, we refer back to the previous previous figure that I have shown. So if we draw this line, we got this type of line, which is the red one, we call it the potential line, and then the blue one, we call it the stream line. So it's constants along the line for both potential flow and stream line. Okay, so this is, we know this is okay. We have constant streamline, which is this, let's say psi 1, and then we have psi n here, and then again similar to this, we have the phi 1 till this one phi n. Right, so this is what we have in the streamline and the potential line, or we call it the equipotential line. All right. So next, the example, you can see my video for example. made a separately video, so you can see this video I solved already this example.